In this video, we're going to explore the composition of functions of several variables. And composition here means linking a series of functions together. For example, imagine we start with what we've been looking at most recently, a function z that depends on two input variables, x and y. Now next suppose that x itself is actually the output of some function of time. And likewise, the y function, or the y variable here, is the function of a fourth variable, s. That's a perfectly reasonable composition where we build the function we're computing out of two inputs, but each of those inputs is in itself developed out of a third or a fourth variable. So we can talk about h of s, or we can talk about y, and that will act as the second input to our function f. Another scenario that we can look at, and this is actually more typical, I would say, is that we have x and y again as the inputs to our major function f, but x and y individually are also functions of time. And so this is a nice analogy for walking on a map, x and y being the location, but that location changing over time, and then some other value, let's say our height, being the output of all of that. What we can do is draw diagrams for these scenarios where, in this case here, time is giving us information about x, or dictating what our x position is, and likewise that same time value is dictating what our y position is. And once we know those two coordinates, then we can compute our f of xy or our z value. A similar situation arises here, only this time with our t value that only dictates what x is. If we want to know what y is, we have to go to the fourth variable there, s, as in serpent, and then once we have x and y, we can run those through our function and get our z values. So again, it's this chaining, it's this linking of functions from some true underlying variables to intermediate variables to a final variable of interest. To make this more concrete, let's imagine a scenario from chemistry. We have the relationship between pressure, volume, numbers of moles of a gas, a constant, and the temperature. Those are all interrelated. We're going to simplify our lives a little bit here and only use 1 mole, so we don't have to worry about that factor. And what we're asked to use is the fact that the pressure is changing per second over time, and the temperature is increasing, over time. And what that's telling us is that time is affecting the pressure, and time is affecting the temperature. Based on those two variables, we should get a statement about the volume. We should be able to tell how the volume is going to be changing back with the original underlying variable here, which is time. The kind of information we would have on that is, if we take a look at the units here, this would be naturally expressed as the derivative of pressure, kilopascals, per second with time. And likewise, this expression here is capturing the temperature rate of change with respect to time. And so what we're looking for in this kind of scenario is what would be the consequence for the volume rate of change. We'll see that in the next page here. Imagine we had some information about the actual pressure and the actual temperature, and then we combine those 4 pieces of information, the rates of change of pressure and temperature, the actual or current pressures and temperatures, and use all of those together to get the rate of change of volume. It's not immediately obvious what that would be, so we're going to explore the technical details of linking these properties or linking these derivatives in a chain effect, so the chain rule, in multivariate calculus. We'll see that in the next few videos.